Okay, should we begin the lectures? First of all, I put the evaluation from the midterm on the course pages in It's Learning. So if you want to see how many points you got, you just go there and have a look. I didn't put a grade on it, but well, you get the idea. It counts 20% of the total total grade, of course. So you get some idea where you're if you did well or not. Today's topic is well, we're going to move on in potential theory if we have time, but first we're going to go into a mathematical detour. We're going to look at something called Green's functions, and George Green was a miller of profession, møller på norsk. So he worked in early 1800s in a mill in Britain. He went to school for 1 year as a child. He was 8 years old or something like that. He taught himself how to solve partial differential equations, starting from essentially nothing, which I think is impressive. But he also made important contributions to the theory of mathematics. And his perhaps best known contribution is well, the Green's theorem, which you've heard about before, I think, and the Green's functions. And the Green's functions are primarily useful when we want to solve a linear partial differential equation with boundary conditions on the following form. Some linear operator L on some function y of x is equal to some source term. So it's a linear operator here. And y of x is our unknown function. I say y of x here, but in general it could be in 1 dimension, 2 dimensions, 3 dimensions, 3 dimensions plus time, and so on. There's no, well, the math is the same, so to speak. So the linear operator, and S is the source function. Now, the brilliant thing here is that ordinarily, when we see this equation, we'll try to solve it, right? So we write down what is S of x, what's the linear operator, and then try to find y, given some boundary conditions. And then we find a solution. But now what if someone changes S? What if you want to find the solution for a different source function? Well, then we have to go back to the equation and start from scratch again. The genius of George Green was to invent a function which made this a lot easier. He essentially said that, well, if I can solve this for a simple source function, I should be able to use that in my with another source function to avoid duplicating the work. So he was a lazy miller, but laziness is a good motivation. Okay, and this is fairly abstract, but to get an example, let's go to electrostatics. To see what we're really talking about. And let's look at the Poisson equation. It looks like this. Laplacian of V is equal to minus rho, let's see, of R by epsilon 0. In this case, the linear operator L is simply the Laplacian. Okay. The y, the unknown function, is the potential V, of course. And the source function is the electric charge distribution. Let's see, that's minus rho by epsilon 0. Okay. So you see the structure of it. There's some linear operator, which could be, for example, a nabla or some similar operator. We're looking for an unknown function. We know what that is. And then the source function is the right-hand side, the driving term, if you want. This is the thing that makes the equation come to life, right? If I try to solve the Poisson equation with no charges, and let's say the boundary conditions is that the potential is 0 at infinity, well then the solution is 0. So we need something here for something interesting to happen. Okay. So as I said, could we try to get some information about this equation and its boundary conditions so that we don't have to resolve the equation every time I change the source function, which could be, let's say, a charge distribution. And the trick is to use the Green's function. And the Green's function is defined by the following equation. It's the linear operator on G, the Green's function of x prime is equal to the delta function of x minus x prime. So I tried to solve the equation defined by well, the same equation as before, except that I put a point source function, okay? And then later I want to try to integrate over the solutions of point source solutions using the superposition principle. And this demands that L is a linear operator. Otherwise the superposition principle doesn't hold anymore. Okay. So same as 1. So I solve the same equation with the same boundary conditions, but with a different source, a point source. Okay. We could also assume that there is some homogeneous solution, which looks like the following. Let's say it could be a homogeneous solution. And the homogeneous solution is characterized by the linear operator on the homogeneous solution is equal to 0. Because if I add the homogeneous solution to a particular solution, it doesn't matter because L on y naught is 0. So if, let's say, V is V naught plus some plus the particular solution, well then it doesn't matter if V naught is there, so to speak, in terms of the equation, because Nabla square of V naught would be 0. Okay, you know this from ordinary differential equations, so it should be known material. So there could be a homogeneous solution. Green's function is only going to help us with the particular solutions. Okay, and then the full solution of 1 can be written as it's y of x. The full solution is equal to the homogeneous plus the particular solution, gx prime, g of x prime, s of x prime. And there you go. If I find the Green's function, I can insert any source function. And then I can, just by solving this integral, I've solved the whole thing. And I can prove that this is a solution simply by inserting into equation 1. Let's see, so I operate with L on y. On the left-hand side here. On the right-hand side, that's these two terms. So it's first of all L y naught of x plus the integral. Let's see, so it's L on the integral, dx prime, g of x prime, S of x prime. I can move this inside the integral because it's a linear operator. So the first term is 0 because it's a homogeneous solution. So by definition, it fulfills the homogeneous equation. So I get a 0 from that term, plus something that's not 0. It's rather integral of dx prime. Let's see, L g of x prime s of x prime. And the linear operator operates on the non-primed coordinate system, right? If it's a derivative, it's dx, for example. It's not dx prime, meaning that this factor here doesn't contribute anything to the linear operator, let's say. So I know because this function satisfies this defining equation here, that L operating on G will simply give me a delta function. And a delta function is really easy to integrate over, meaning that I get out. We only got a contribution when x is equal to x prime, so I get out s of x. Okay, so it's easy. Just insert the suggested solution into equation 1, and we've seen that it's a solution. Now the question, of course, arises: what's the Green's function? How do I find it? Because this is all very nice, but if you can't find the Green's function, it's not very helpful. But you see the point? If I now solve this equation, I can immediately write down any solution to equation 1 on this form. I just need to find the Green's function, and I can just integrate over the source function. I know all the solutions that exist. Let's see. So I'm just going to write down the defining equation for the Green's function, so you remember. L on G of x prime is equal to delta x minus x prime. Okay. Now, as an example, we're going to examine the Poisson equation because we know what the solution is. And then we can see if we can find out the Green's function by, let's say, going the other way around. And if we start off with the Poisson equation again, nabla square of v is equal to rho over epsilon naught. We stay in the vacuum today because, well, the material complication doesn't change the mathematics much. So just to get the idea, we're staying in a vacuum, so epsilon 0 here. And the solution we found previously in the lectures to be, let's see, 1 over 4 pi epsilon naught integral over d3 r prime. The boundary conditions are, I didn't state them explicitly, but the potential should be 0 at infinity. That's our boundary condition. Now rho of r prime over big R, or let's see, r vector minus r vector prime. There you go, the well-known solution. And as we saw, L is the nabla square, S is 1 over epsilon naught rho, and Y is V. And if I compare that to the Green's function solution, well, then I just stare at this equation here, I see that rho over epsilon naught, that's the source. This is the unknown function. So what's left must be the Green's function, meaning that g of r prime, now vector-based because it's in 3 dimensions, is 1 over 4 pi 1 over r minus r prime. That's the Green's function for the Poisson equation. Let's see, maybe there should be a minus here. Any questions? Is this perfectly clear? Okay. So we found the Green's function for the Poisson equation, but we found it by knowing the solution, which kind of ruins the point. So we want to be able to find the Green's function for, let's say if I gave you a new equation, you want to find the Green's function for that equation without knowing the solution. And one trick to do that is to start off by looking at the equation and expanding the Green's function into looking at equation 2 and Fourier transforming that equation. So we start off by looking at Lg of x. Now let's see, I'll work with the Poisson equation as an example. So it's nabla square of g of r prime is equal to delta of r minus r prime. So we have a r prime, and this nabla square works only on r. Okay? Now I will expand this Green's function, which is unknown, into its Fourier components in the following way. G of r prime is equal to 1 over 2 pi to power 3, because we have 3 dimensions, an integral of g of k. These are the Fourier coefficients of the Green's function. Then the plane wave, e to I k r minus r prime d3 k. Note now that the Green's function is actually only a function of r minus r prime because of the symmetry here. This simplifies things somewhat. Okay. So I Fourier expand, and I remind you that you can write the delta function as the following Fourier expansion. Delta of r minus r prime is equal to 1 to 2 pi to power 3 d3k e to I k r minus r prime. There you go. So that's the delta function in the Fourier domain. And we insert this into this equation. So we get an integral on both hand sides, both the left hand and the right hand side. So it's the Laplacian on this integral. And I can take away the 2 pi's because they're on both the left hand and the right hand side. So it turns into g of k e to I k r minus r prime d3k is equal to this integral e to I k r prime, like that. Okay, now this looks a bit terrifying at first, but we realize that we can just move this on the left hand side, and no, wait a second. Okay, first of all, what's this nabla on this integral? And note that this is on the, with respect to the unprimed r's. So it's this r here. That's the only one we need to calculate. And it's it's linear, it's a partial derivative, meaning we can move it inside the integral. Let's see, the notes are a bit messy, but anyway, what we need to find out is the nabla on this plane wave, or the Laplacian rather. So let's see, Laplacian on the plane wave well, if I just look at the Laplacian, it's equal to di, like this, the nabla dotted with itself. And if I just look at one of these at a time, well, then I can look at dx. So let's see, dx square of e to I, and then it's, well, actually I can just take this one away, because I could just factor out that term, making it even easier. So it's dx square of e to I k x x plus k y y plus k z z. Partial derivative of this function, it's an exponential, so it's rather easy. It's in fact minus k square of e to I k r. Like this. If I do the same thing with respect to y, I mean dy square, I will simply get down ky. And if I do it with respect to z, I get down kz. Let's see, it should be an x here, meaning that the Laplacian of e to I k r will simply give me minus k, let's see, kx square plus ky square plus k z square, and then the exponential back. And this is simply the length of k vector square. So it's k square, like that. Or more compactly, Laplacian of e to I k r is minus k square e to I k r. This is of course the whole motivation for going to Fourier space, because now what was once partial derivation in 3 dimensions, it's now simply a multiplication by k square. And if I now take this and move it on the left hand side, and I insert my, I know what this is now. If I insert that into the integral, I will get that the integral of d3k, and I have g of k times minus k square from the derivation here. And let's see, I move the delta function on the left hand side, so I get minus delta of r. No, wait. Delta function is simply 1 in the Fourier space. And this should be equal to 0, because I moved all the terms on the left hand side. And this should hold for all k. So if this integral is to vanish whatever the function g of k is, well then this bracket has to be equal to 0. And this gives me the condition to determine what are the Fourier coefficients of the Green's function. And if I know the Fourier coefficients, I can surely find the Green's function by doing the inverse transform. Okay, so this equation to solve now is g of k, k square plus 1 is equal to 0. So my original partial differential equation is now reduced to simple algebra. In principle, there should be k vector here, but we see from this that the only dependency is on the length of k, which is to be expected. Because we have spherical symmetry in real space, you get that in Fourier space as well. So g of k is equal to minus 1 over k square. And now in principle, I now have the Green's function, because knowing the Fourier coefficients or knowing the function itself is equivalent. But in the end, if you want to get something practical out of it, we need to be able to solve this integral. So let's see if we can do that, and then we've shown that the Fourier trick was worth all the hassle. By the way, it's nice if you stop me and ask questions, because I realize this is probably new stuff to all of you, with perhaps a few exceptions, but I don't think any of you have seen this before, right? So just stop me if there's something that's not clear, because Green's functions are very useful. So you do want to understand them. Okay. Now, I wrote the Green's function of r prime as this integral 1 over 2 pi to the power 3 g of k. We now know that there's no need for the k vector because of the symmetry. E to I k r minus r prime. And we found that g of k is simply minus 1 over k squared. And we need this dot product here. So let's draw a figure. If I have the function r minus r prime, let's say along the vertical axis in some coordinate system, well, then the k vector is pointing like this, and the angle between them is this polar angle theta. In principle, you could have some phi dependence, but you don't in the dot product, because k dot r minus r prime, well, if I just choose my coordinate system like this, then this is k length of r minus r prime. Actually, that should be the length, and cosine of the angle between them, which I call theta. And then I think we have all we need to solve this integral. So let's see. Well, this is just blood, tears, and hard work. So let's get started. G of r prime is equal to the 2 pi's. And it's minus 1 over k squared. E to I k r minus r prime. Let's see. I write it like this, cosine theta, k squared dk d omega k. This is the space angle, and this k squared dk is the contribution from the small volume, essentially, in spherical coordinates. Because as you can see, because of the spherical symmetry, the integral is easier to solve in spherical coordinates, of course. Okay, this turns into minus 1 over 2 pi to the power 3. And I can see now that there's no phi dependence. So there's 0 to 2 pi d phi. This factor is simply equal to 2 pi. And then I get the integral from 0 to infinity dk. The k square over there and over here cancels. So I don't need to worry about those. And I will do the angular integral first, from minus 1 to 1 e to I k minus, let's see, k r minus r prime. x dx, where I did some substitution, namely that x is equal to cosine theta. You recall that this contains sine theta d theta. If I just change to x is equal to cosine theta, which is, let's see, that's this cosine right here. This integral is really easy because it's a constant with respect to x times x inside an exponential. Yep.
Yeah, I've got this one integral over k.
This one?
Yeah, but what's the with the e of with the e to I k?
And the length of r minus r prime.
Yeah, but the k is still there with the exponent.
Yeah, k is still here. So first we do the angular integral. The phi's are easy because there's no phi dependence. And the cosine theta stuff, well, that's, if I do the substitution, it's simply e to some constant times x dx. So it's quite easy integral.
Okay, so you have this integral and the k integral.
Yeah, so this integral, let's say, yeah, I integrate everything following. This is common notation in physics, but perhaps not in mathematics, that you put the integral and then the differential. If you want to integrate everything behind it, it's a nice notation, I think, because then we see what variable am I integrating from 0 to infinity. If you have 3 integrals first, and one of them is from 0 to infinity, and then you have to go to the right-hand side and figure out which one has the limits. So it's just a notation, yeah. So I want to integrate all of this behind here with respect to phi, k, and x, or theta, equivalently. Let's see. Yeah. Was that okay now? Good. So we got out a 2 pi here, which gets us rid of 1 here. It's 1 over 2 pi to power 2. Phi integral is gone. We're still left with 0 to infinity dk. And this integral was quite easy. It's just an exponential, so it's e to I k r vector minus r vector prime x over I k r minus r prime from minus 1 to 1. And now we're out of space. Let's see. So we almost solved this integral. This e to ikx over ik, well, that's simply the sine of this stuff, right? Because the sine of x, let's see, sine of x is equal to e to ikx minus e to minus ikx over, no, ix over 2I. You know this from before, right? So this becomes sine of something over something. More specifically, 1 over 2 pi. Square is still there. And then there's a factor of 2 coming from here, essentially. Integral over k. Still haven't done that one. dk. Sine of k r minus r prime divided by k r minus r prime. So it's a friend, the sinc function. That's of no importance. There should be some minus sign cancelling this minus sign. I guess it's from this sine function stuff, I hope. So 1 over 2 pi square. Now there's 2, cancels one of those 2's. And let's see, I can rewrite this as 0 to infinity, and then 1 over r minus r prime d set sine of set divided by set, and I did the substitution. Set is equal to k r minus r prime. So it's k r minus r prime, like this. If you look carefully here, you see that there's no r dependence in set, or well, actually there is, but we're integrating over k, right? So we don't care about this. It's just a constant, meaning that I can just move this factor outside, and it's a well-known fact that the following integral, 0 to infinity dx sine of x over x is equal to pi halves. So this 1 over x makes sure it decays, the sine makes sure it oscillates, and the integral converges to pi halves. So the integral just gives me pi halves, and I get out the Green's function. Finally. And it's equal to minus 1 over 4 pi. I think there should actually be a minus sign here. But never mind the prefactors, right? So r minus r prime. There you go. We finally found the Green's function for the Poisson equation. And now we can just write down the solution to the Poisson equation. Well, it's simply the integral over d3r, the Green's function, and then the source as a function of r prime, so it's rho of r prime divided by, divided by epsilon naught. And I now know what the Green's function is, so I just conclude that the potential can be simply calculated by solving the integral d3 r prime rho of r prime divided by 4 pi epsilon naught r minus r prime. And if you want, you can take this and move it on the outside to get it on the standard form. So this was a lot of math, but what did we do? We started off by looking at this equation over here, number 2, where the linear operator is the Laplace operator, and the delta function is the delta function. This defines the Green's function. I take the Fourier transform by writing it. Well, actually, this is the inverse transform of g of k, right? So g of k is the Fourier transform of g. But I just write it as an expansion in plane waves. So it's stuff you know from before. You can expand a function in a complete set of basis functions. These are the expansion coefficients. In this Fourier space, it turns out that differential operators were really easy. They were just multiplications by k, which gave me an algebraic equation for g of k. And I found that g of k was minus 1 over k squared, just by solving a simple algebraic equation. I can then conclude that, well, all I need to do to get the Green's function is to perform this integral over g of k. I now know what g of k is, so if I can solve the integral, well, then I found the Green's function. And once I found the Green's function, well, then I'm happy, because now I can solve any Poisson, let's see, I can solve the Poisson equation for any right-hand side as long as I can solve the integral. Any questions?
You said you had a boundary condition?
Yeah. I think I said it, but it was perhaps not clear. V of r should go to 0 as r goes to infinity. This is a typical setup, right? Which we discussed before. If, let's say, I have some, if I put this inside some box, let's see. Well, we did this because it's a very general setup. And you can, well, there are many problems you can solve by this. For example, if you have some small particle, let's say in a solution of water, then you shine light on that particle, what happens? Well, then the typical boundary conditions is that something comes in and something goes out, but there should be 0 potential at infinity. So it's kind of a textbook problem in one sense, but also it can be used to solve real problems. Let's say if you took some different boundary condition, let's say I have a box. We did something like this before in electrostatics, right? We have some metal box, and let's say I put some charges inside the box, and then let's say I put some potential V not on this side of the box, but keep the others at 0, for example, on the surfaces. So there's some non-trivial boundary condition problem to solve. Then we need to add the homogeneous solution first of all. So it could be that, let's say, nabla square of V is equal to 0. Well, Vc, some constant. V naught is some homogeneous solution. This would need to be satisfied. I mean, we solved an equation like this in electrostatics, right? But in addition, we would need the Green's function and integrate over the charge distribution to find the particular solution. So V is equal to V naught plus Vp, the homogeneous and the particular solution. The Green's function is, of course, subject to the same boundary conditions. So when we solve nabla square of G of R prime is equal to delta of R minus R prime, well then G needs to satisfy the boundary conditions as well. So if the potential should be constant on these boundaries, so should the Green's function. But to solve the Green's function for what is more or less the most general case to, well, it's a good example of the use of a Green's function as well as being relevant to this course. Yeah.
Will boundary conditions play into the V of k just as in ordinary Fourier?
Yeah, because if you change, so let's see, G of R prime is equal to the integral over dk, let's see, d3k G of k e to I k R minus R prime. This is what you're talking about, right? So if I change the boundary conditions, will it change G of k? That's the question, right? Well, the Green's function needs to satisfy a different set of boundary conditions now. So the Green's function is going to change. And knowing the Fourier coefficients of a function is equivalent to knowing the function. It's simply a different representation. It's like quantum mechanics. If you're in position space or momentum space, you don't care. You have the same amount of information. It's just that, for example, operators look different. So yes, if you change G, you change G. If you change the Green's function in real space, you change it in Fourier space too, because you can't change the one without the other. There's some proof saying that there's a one-to-one relation. If you have one Fourier set of Fourier coefficients, that's equivalent to knowing one function and vice versa. There's a one-to-one relation between Fourier space and real space. That answers the question?
Yeah, but don't you have like an explicit formula for how the G of k changes with the boundary conditions?
No, not really. Well, it's going to depend, well, no, but you could write it on this form. let's say if I call it G prime, because I changed the boundary conditions, and then I could solve this equation as well, but then I would need to satisfy the boundary conditions in some different way. So, yeah. There's no, I don't think there's any general way of doing that I'm aware of. Anything else? Okay, then we take a break.